Hello there, great person. Welcome to another science video reaction. I'm a physicist, so I'll react to this video as someone who knows probably a lot of the stuff that they're going to talk about. I'm also specialized in quantum physics, so this one will be more in my area of expertise because it's called quantum superposition explained without woo-woo. And it's often explained with that. So I'm quite interested in this, and it's from Science Asylum, one of my favorite science channels. So popped up in my recommended feed, and I just said, yeah, why not do it this week? I didn't have a video for this week, and I'm looking forward to their explanation. So as always, I will pause in between, give you my comments, because I want to give them immediately because I will forget them otherwise. And yeah, anything else? No, I don't think so. Let's just get into this. And if you like this, consider liking and subscribing. And you can apparently ring that bell. I don't know what it does. So have some fun with this. Let's see.
The quantum spin of an electron is the quintessential example to use here, but that can get confusing real fast.
This is better.
It's like a ball that's spinning.
No.
Except it isn't a ball.
And it isn't spinning.
And it isn't spinning.
I love that joke so much.
So to keep this explanation as simple as possible, we're going to remove all that baggage.
That joke.
Like the photon, we're going to be traveling light.
Yeah, a photon, by the way, is also not a ball. It's also not spinning and traveling. Yeah, you might argue that, but not like a ball.
No electrons, no quantum spin, no none of that stuff. We're talking about
polarization
balls in the land of make-believe.
Yeah.
Actually, I probably don't want to say balls a million times today. We're going to be talking about orbs in the land of make-believe.
Yeah.
These orbs come in two different textures, smooth and rough. But texture is on a spectrum measured by the coefficient of friction. I know, but this isn't the real universe. It's a metaphor. Just go with it. Okay, we'll see where this goes.
Metaphor, that's the thing. Everything he's saying is a metaphor, and I love his channel for this because he's always doing it like that. He's always saying, this is a metaphor, it's not how it is. It's a metaphor. And the ball thing is a metaphor as well, so I'm actually quite happy already.
Thank you. These orbs are not stuck in their state. We could send a rough one through a polisher and it would become smooth. We could send a smooth one through a roughener and it would become rough. So if we wanted to, we could change the state of any of these orbs. Generally, though, we're not trying to do that. But what if they're not just orbs? What if they're quantum orbs?
Yeah.
You might imagine a third state that's both smooth and rough at the same time. Something we'd call a quantum superposition.
That's not correct. It's not at the same time. Something completely different. I hope he's gonna explain it that way, because that's the crux. Quantum superpositions, they're not at the same time. It's not like that. It's like saying, yeah, it's not blue or yellow. It's something. It's both blue and yellow, and what your meaning is red. You know, it makes no sense like that. But let's see what he does. I think he will probably explain it correctly in a moment.
Visuals like this are misleading, though, for multiple reasons.
Yeah.
First, they give us the impression that these new combination states are somehow multiple states at the same time.
Yeah.
Which they're not.
Yeah, exactly.
That's not how this works. That's not how any of this works.
Yeah.
Even quantum superpositions are single states. We might not intuitively understand them, but they're single states nonetheless.
Yes,
Second,
very good.
Visuals like that make it seem like there's only 3 states available, when there's actually an infinite number of possible states.
Yeah.
There are infinity minus 2 possible examples of this kind of state. It's not the weird one.
Yeah, -2 because of the 2 on the left. Yeah. I will, in the end, I will tell you how I would visualize it. I actually did this in class last week.
These two are. Quantum superpositions are the norm. To understand what's going on here, we need to do a little review of how vectors work.
Vector space.
If you're not familiar,
Spooky.
vectors are just quantities that have a direction. They're usually represented as an arrow, like the velocity of this cookie.
Yes.
Let's pause the animation for a moment and say
It's
this
flying.
cookie is traveling at 5 miles per hour this way.
Quite a quick
If we
cookie.
impose an
Why is
XY
it
plane
cooking?
on the picture,
What does it want? Where is it going? What's his life's purpose? Or its life's whatever.
We
Sorry.
can define a couple special vectors, one along the x direction and one along the y direction. These are what we call basis vectors.
Yeah.
Because they're the basis of any vector in the xy plane. Surprisingly, the name makes sense. We can write any vector in the xy plane as a combination.
I don't even
of
have to
these two
stop it.
basis vectors.
He's explaining it
Velocity,
perfectly.
That might be 3 miles per hour to the right and 4 miles per hour up.
Yeah.
The set of all vectors that can be written in terms of these basis vectors is called a vector space.
Yeah.
There are all kinds of vector spaces, some more abstract than others. See, vectors are just a mathematical tool, and sometimes tools can be used in unexpected ways. You know, like opening a walnut with a sledgehammer.
What are you doing,
Anyway,
May?
the
What
coordinates
was
we used for the cookie
What
measure
was
location,
that?
so we call it position space.
Yeah.
Or since it's the default, sometimes we just call it space.
Also interesting, and this is more of a tangent than me commenting on this. So in quantum physics, there's the two main spaces are position space and momentum space. And the interesting thing is that every measurement you do is it's in some space, you know, but it's also mostly in position space, and that's why we have this idea of space, which he says here is space, yeah, because position space is the space, you know, like a room, or I don't know, a park that's position space because there are positions in it. You can put a coordinate system into it and you can describe places. So, but there are other spaces. So if you measure something like with the double slit experiment and you measure where it hits, you also measure position space. It's nothing. You measure like you measure one of the states, but you measure it in position space as well. So you can measure more than one quality, and if you do all these experiments that you see on these channels, you always, not always, in most of the cases, you also measure position space. There's also, yeah, momentum space. That's something as well. And by the way, the relation to between momentum space and position space can be really interestingly visualized by using or for using the Heisenberg uncertainty principle. I like that a lot. I do that often to visualize it via these two spaces. Well, this space and the one I mentioned.
It might be the only space you see in introductory physics, but there are plenty of other options. In my master's thesis, I used momentum space to model electrons in a white dwarf.
Whatever. I'm an idiot.
Even momentum is an obvious vector, so it's not too much of a stretch. Quantum mechanics uses vector spaces on things that aren't vectors. Speaking of which, let's get back to our quantum orb. What if we chose one direction to be smooth and the other direction to be rough? Instead of texture being on some kind of linear spectrum like NerdClone suggested earlier, the texture state of our orb would be a vector in this abstract vector space. If it's in the smooth state, it looks like this. If it's in the rough state, it looks like this. These two vectors are the basis vectors for our texture space.
They're also called the eigenstates because...
Whoa. I'm gonna stop you right there. That's a whole other video. We need to stay focused on the topic at hand.
It's important though that when you measure it in one, it's like you say, is it X or is it Y? And because it's nothing, it will like flip to one of those positions and it will have a different state. You know, that's important here though. I think that's important. He'll probably, knowing him, he'll probably explain that again, and I did waste your time again.
What quantum mechanics does is it opens up more options to a physical property. It takes the state of any quantum particle and treats it like a vector in an abstract vector space. Any state of any particle. The length of a state vector is always equal to 1, but the angle can change. That means many states are available to it, not just 2. These are only the 2 basis states. The rest
And
of
you
them
choose
look like
them.
this.
You choose the basis states by how you measure it. That's what you do. That's what the observer does. And with observer, what is meant is like your measurement apparatus or whatever. So you say it's X or Y, I will see if it's X or Y. And then by that you get this coordinate system and you will have these X's and you will get a result on these X's. And depending on which axis or where the arrow is closer to, it's a higher probability that you get it. So if you get if the arrow would be already pointing upward, it's 100% chance that you get that state when you measure it. If it would be this way, 100% to measure the smooth state. And if it's in between, it's it's like it's 50-50 if it's between them. And that's, by the way, why when you send electrons through this Mach-Zehnder spin, it gets one of the two states. So it's like let's say you get it into this state, and then if you measure it into another direction, you like change these coordinates, and you might like do it like this. So you have a superposition again in that state. I really like that. That's the best explanation I know, I think.
All infinity minus 2 of them. There's only ever one state arrow though, so it's only ever in one single state. To take this point home, let's look back at the velocity of our cookie from earlier. It doesn't point along either axis, so it has components along both. Would you say this cookie is in two different velocity states at the same time? No, of course not. It's in a single state, 5 miles per hour in whatever direction it's moving. Another way to look at this is that there's nothing special about this particular XY plane. I could have just as easily drawn it like this, or even like this. It doesn't matter. If the coordinates look like this, the cookie's velocity is only along the X direction.
And doing that, exactly what he just said, deciding the position, that means that you decide what you want to measure. So if it's like this, you measure something different than when it's where it started.
Did it suddenly drop from multiple states to a single state? No, it was in a single state the whole time. We're not changing anything about the cookie itself, just how we represent it mathematically. The same goes for our texture states. No matter what states you're looking at, it's only one arrow. It's always only one single state.
But you can't measure it.
Write it as the sum of two other vectors doesn't change anything. The orb does not care. Just a little note though before we move forward. This notation I'm using is called bracket notation.
Yep.
As in bracket notation.
But you probably know that if
Each
you
state is
read
encased
up
in a
on quantum
bracket.
physics.
When the bracket is on the right, they're called ket vectors. There is a such thing as a bra vector. Yes, it's really called that. But it isn't important until we start taking math.
Why? Because someone wanted to be clever. He said, let's say bracket and pull it apart. Oh God, we've got bra. I didn't think of that. That's how we work. That's how physicists work. I already told about it. If you name something, you're sometimes trolling.
Measurements. If we're going to continue like this with our quantum orb, at some point we're going to want to measure that texture. You could feel it with your hand, but humans are a bit biased. Plus, remember that this is just a metaphor for particles, and you can't feel particles with your hand. So instead, we'll be using a texture detector. Say that 3 times fast. Texture detector, texture detector, texture detector. If an orb is smooth, it'll come out one exit. If it's rough, it'll come out the other exit. So what happens if one of those superposition orbs goes in there? Well, how does that box work? Oh, I have no idea, but it doesn't matter. Wait, where's Nerd Clone?
I called you back up.
I'm getting teamed up on now. Great. All that matters about this box is that it sorts orbs into 2 distinct categories.
And why that is so weird is because you project 4D space into 3D space. It's again the same thing I already talk about. Always talk about. It's like 4D ball comes, and because you can't, because it doesn't point to one of the axes you've defined, so to speak, it has to change, and that's the projection done into 3D space. Again, but yeah.
And it never fails at its job.
Creeped up on me.
On the inside, the box can
So he
work
is
however
avoiding
you'd
interpretation
like, as long as
issues.
it meets those criteria. So let's go through the options. We know the orbs can't split and come out both exits. My orbs are like particles, so they're invincible.
Invincible orb.
Invincible orbs. How is this still sounding like innuendo? Anyway,
That's the thing. I really like this, the way he's phrasing it. The metaphor is for a particle is that it's a quantity. Particle is an abstract meaning. It's not like a piece of dirt. It's not piece. It's particle. Particle doesn't mean piece. In the sense that it's a piece of dust or piece of sand. It's an abstract piece. That's what particle means. And many people think about them as balls, and many elementary particle physicists also do, and works for them a lot. I've talked to some. they say, yeah, we know it's in quantum physics it's different, but for particle physics it's okay. That's all we need. So yeah, it has some usability as well. So
we also know they can't come out neither exit because the detector never fails. That only leaves two options. It comes out exit 1 or it comes out exit 2. A superposition orb goes into the detector and has to pick an exit. In the process, though, it's no longer in a superposition. You remember how the polisher box could make an orb smooth and the roughener box could make an orb rough? Well, the texture detector can do either of those things under the right conditions. Texture detector, texture detector, texture detector. The act of measuring the state of the orb changes the state of the orb.
that means it turns the arrow.
And this isn't because we designed our detector wrong or our technology is limited. Any detector that meets these criteria has no choice but to affect the state of whatever it's measuring.
That's
It
the
doesn't
point
matter
he's
how
not
you
shown
design
yet.
Now, to be clear, neither the detectors nor the orbs are making any kind of conscious decision. The choice is made by physical rules. Those rules just happen to be based on probability. The state vector actually tells us what those probabilities are, and it does it with these numbers.
Yep,
This
that's
is
what
where
I
those bra
told you in the
vectors come
beginning.
in. Say you've got an orb in the smooth state. The chances of it coming out the smooth exit should be 100%, right? Here's the smooth state written as a vector. Taking a measurement looks like this. A bra vector next to a ket vector to make a full bracket.
By the way, you have understood this with the arrow and the it popping to one of the axes and then redefining the axis so that they're not having the arrows on top of each other. So the basis arrow of the base, the arrow of the base, and the state arrow, if they are not on top of each other anymore. If you have understood that, you can watch the lecture from the MIT. It's the Quantum Physics Introductory course, I think of 2017, something like that. And there he has this great experiment with weirdness or something like that. He also has these monkeys in a machine that are sorting it, and the experiments he gives, what he does is like the professor, he says, yeah, what will we measure, what will we measure? And if you understood this, you can answer every single one of those questions. You just need to understand this arrow and that it's changed when you measure it.
Squaring the answer gives us the probability, which is 1 or 100% in this case. We can do the same thing with the rough state. The chances of a rough orb coming out of the rough exit is 1 or 100%. The chances of a rough orb coming out of the smooth exit is 0%. The same goes for a smooth orb and the rough exit. As long as you can remember those 4 options, we can do this with superpositions too. Say the orb is in this state. What are the chances it'll come out the smooth exit? Well, you just use the smooth bra like before. Is it too much?
It is what it is. What are you gonna do?
The bra vector comes in, operates on both terms.
Having way too
we
much
plug
fun
in
with
1 or
this.
0 where needed, square the answer, and bam, probability. You can do the same thing for the rough exit, or just subtract from 100%.
Okay, that's an acceptable analogy.
Thank you. So what's a quantum superposition again?
Review time.
Quantum mechanics opens up more options to a physical property using vectors. Rather than just smooth or rough, our made-up orb can be in any state in this abstract XY plane. No matter what, it's always in one single state. We just don't intuitively understand most of the options. The coefficients of a superposition tell us the probabilities of getting one of the basis states,
Yep.
specifically after passing through a detector that measures those basis states. That's it. That's all it is. And that's true no matter how many basis states there are. I kept my example at 2 for simplicity, but it depends on the circumstances. You could easily have an infinite number of basis states.
Yeah.
The point is, though, if someone says a quantum particle is in more than one state at the same time, they're either not fully embracing the nature of quantum mechanics, or they don't think you can. So, did
yeah,
this help you understand quantum?
very nice. Give him a like, please. He's so good. So exactly. So there are many people who say that, and either they don't know, or they think you're stupid. I can't imagine I'm with him. I can't imagine any other way why you would say it like this. It's so misleading, so misleading. So I will explain it again. I will just use some pens. Do we have enough? No. I don't. Okay, let's do it like this. So I will take the sonic screwdriver. I've got it lying around currently. So yeah. So I will just, this is the state. So let's say the state is the sonic screwdriver. If you measure it like you have this axis and this axis, and you measure it, it might go this way, So every time you measure it now, it will always be this because it has flipped and it's 100% chance, so it stays that way. Let's say you measure spin up or and down, like in the z direction. So you want to measure if the spin points up or down, and I mean that literally. So in space, is it up or down space? So you measure it and it goes to spin up. Okay, so every time you measure it, it will be spin up. Now you say you want to measure if it's left or right. So because 3 dimensions, you have spins, so to speak, in every direction. But let's say you now measure it left or right. It's like saying, yeah, okay, I take my arrows away and I put them like this, but more like this. So if you measure that, it pops again here or here because, it switches again. And then if you, let's say you measure left and it's left again. And if you now measure up again, it has to snap again, So that's why it's random again. And you can see that in the operators, like in the angular momentum operators, the spin operators, that's what they do. That's what they are. And this is a bit more technical, so if you're already a bit into this, it's like the commutation rules there. So anyway, I hope you liked this. I hope it was not too confusing in parts because it's hard to explain without drawing it. But yeah, I like his videos a lot. This was a very good video. I don't think he really did something where he said, yeah, you have to be careful. He just could have told you more, I think, a bit. But I mean, he's on a budget and he has to keep it short because many people don't pay enough longer spans of attention, unfortunately. That's the thing nowadays. But yeah, for what he does here, very nice content. So give him a like, subscribe to him perhaps, and I will see you in the next video. Have a great Thursday, and Wheel of Time will probably be out, I don't know, in 5 hours or so. See you around. Bye.